Okay, so from yesterday's example, okay, we dealt with, what was it, aluminum? Okay, well, as you look up at the board here, look at that graph diagram that we have. We're dealing with what, don't say H2O, what substance are we dealing with? Okay, so when we say that, water exists in how many states? Okay, water in a solid state is called what? Ice. Water in a liquid state is called water. And then water in a gaseous state is called what? So, that's why you see ice, water, and steam. Remember, we said yesterday, when we changed aluminum from a starting temperature to a final temperature, we went through all these different phases. One, you raised it to its melting point. Then you melted it. Then you raised it to its boiling point. Then you boiled it, and then you finally vaporized it. And it would not make any sense to talk about vaporizing water in the first step, would it? So what we see here in that diagram, in the lower left-hand corner, that says negative 35 degrees Celsius. So what state is water in? Freezing. Well, it's freezing. It's a solid state. Okay? So in these 5 steps, that's why we kind of ran out of room yesterday. So when we look at this, there's 5 steps or 3 different formulas that we use. Okay? So in steps 1, 3, and 5, we do what formula? Q. Okay? So for those of you who are gone, Q measures what? Heat, or the quantity of heat in what variable? Joules. M is a what? It's a mass of that substance measured in grams. Okay, C subscript P is a specific heat, which means it's how quickly, okay, a substance either it will heat up or cool off, because as you can see, it's measured in a joule per gram degree Celsius. So depending on how big it is, the mass, the temperature that you're measuring that at, and how much heat it takes, how quickly it goes up or down. Okay? So for instance, when we dealt with aluminum, it could be aluminum, copper, iron, any one of those, the specific heat of that is so low because what do metals do very efficiently? They conduct heat and electricity very well. That's why their specific heat is so low. It takes so little energy for that to conduct. Yeah, to put it into that it takes energy, but for it to conduct it, it does not, because it is such a good conductor. Okay, and then triangle T then means what? Temperature range or change in temperature, which if you want to be more specific, you could write what minus what? The final temperature minus the initial temperature. Okay? So again, that is steps 1, 3, and 5. Okay? Then what we see happening in steps 2 and 4, okay, the amount of heat or quantity equals that mass times what? The heat of fusion in step 2, or the heat of what in step 4? Vaporization. Okay. HV. Okay. So we really don't need this H2O in here. We just wanted to illustrate that water or H2O exists in three different states: a solid, a liquid, and a gas. Okay. So, in step one, okay, look at where we're at, minus 35 degrees Celsius. You correctly said that water would exist in a solid state, or it's ice. So, what we need to do to get from negative 35 all the way up to 156, first, we need to raise this temperature until it does what? And that will occur approximately at what temperature? 0. Well, 1. But once it gets past 0, it's going to start to melt. So, in step 1, we know that the quantity of heat equals the mass. So you need to give me a mass of this water, or 674. Okay. So, with that, in step 1, or Q1, that 674 you just picked, okay, what is the specific heat for H2O in the solid state? No, all the information you need is up on that board. No. What is the specific heat for H2O in the solid state? 2.06. How did you know that? Did you just make that up, or it's up on the board? Okay. Okay. So, what does C subscript P mean? Specific heat. Okay. Do we agree upon that? This is yes. This is no. Do we agree upon that? Okay. So we agree that C subscript P means specific heat. Okay? So the specific heat of H2O in the solid state is 2.06. Yes. Okay. So, in this case, what do we do with these two numbers so far? They're next to one another. Okay? Now, what is our temperature range? We started at negative 35, and you got to go to 0 because that's when ice starts to melt. So, what is the temperature final minus temperature initial? In other words, 0 minus a negative 35 equals 35. Okay? So we got 35. Okay? So that is Q1. So what do we get for Q1? Do you want to go back and do it on your own time, or you want to work on that together? Okay? 4, 8. 5, 9. And what's that labeled in? Joules. Okay. Q2, or the quantity of heat, is going to be that same mass. Okay. What is, now that we've raised it up to here, this was Q1 because we raised it up to its melting point, which was 0. Now, from this to this point, notice the temperature isn't increasing. You'd say temperature is over here, okay, and then I suppose heat is down there. But that's just one way you can look at it. We're not concerned about this independent axis. We're more so concerned about the temperature over here. So, in step 2, quantity equals mass, which we put in there. What is the heat of fusion for H2O? 334. Yes? Okay, so when we multiply them two,
You get 674 times. Oh no, you get you get 225116. What? No, that's what you meant.
okay,
No, I was saying it like out loud and I didn't
now
hear the right sound.
Q3,
Oh, start from now.
674. Okay, now we're up to this third one. So now that we have done this, we've melted it. Now we go from this 0 up to here, which is 100. Okay, so in this case, what is the specific heat of H2O in the liquid phase?
4.84.
Okay, 4.84. Okay, what is our change in temperature here? 100. So one way to look at that is you are subtracting the melting point from the
Melting point from the liquid point, the 0 point.
from the boiling point. Okay? Because we know that H2O does what at 100? Boils. What does it do at 0? Well, that's when it freezes. So Q3 is what?
You get 326216.
Okay? Joules. Step 4. Now we are going to start to do this. Q4, 674. Okay? In step 4, mass, not times heat of fusion, we did that already. Heat of vaporization, which is what?
260.
Okay? So now, you multiply them too.
152324.
Okay? And then finally, in our last step, Q5, now that we began to boil it, what's going to happen when it gets up to this temperature? We call it what? Yeah, it's vaporized then. So water went from a solid state, Q1. This one was Q2 because we melted it. Now we're going up to boil it, Q3. Now we're boiling it, Q4. Now way up here, Q5. Okay? 674. 2.02. Okay, because in this phase we subtract our final temperature from where that substance started to boil, which was 100. So 56. Okay.
We would get
7.6.
242.88.
And then finally, QT or Q total would be what?
So we 1 through 5 add all of them.
Once you get them, the Q total is adding all them together. Yep. 4859.
No, I'm just thinking.
Okay.
I have to think out loud.
Me too. We'll do it together, maybe.
What do I need? I got 2199.
2199.
410.28.
That's what I got too.
Okay. That's it. All of these added together.
That's all the Q's added together.
Yep.
We just label it.
Joules. Yep.
So it's not
All energy is labeled in joules. After James Joule.
The question would just ask, how much heat will it take to get from the -0.5?
Right. So this word problem would be quite extensive, unless, but with this one, I'm going to leave that blue and red information up there because in a story problem that you have, it doesn't have all those written. So what I mean is, so I'll get the stapler. We'll find a problem that is similar to this that has all that information so you can point out what it's asking or looking for.
And if a specific temperature is -1 kilogram over both gaseous.
what is
I have an extra one here. Somebody not get one? Oh, okay. I should have made an extra copy. Okay. So on this second one, the one that's in the back, okay, it says, we're talking about copper here. Okay, it's the second paper, the fourth one down. It says how much heat required to raise the temperature of 675 grams of copper. Okay, do we see where we are at? Okay, and it says from 900 degrees to 2700 degrees. Then it goes on to talk about the specific heat of liquid copper is 0.385 joules per gram degree Celsius. The specific heat of gaseous copper is 0.314 joules per gram degree Celsius. The heat of fusion is 210 joules per gram. The specific heat of solid copper is 0.396 joules per gram degree Celsius. And finally, the heat of vaporization is 4783 joules per gram. Now, there are two numbers you are missing there. The boiling point and the melting point for copper. So you need to write these two numbers in there. Okay, and that would be as follows. Copper's boiling point, melting point is 1085. So MP equals 1085. BP, or boiling point, equals 2570. Any repeats on that? MP, or melting point, is 1085. Boiling point, or BP, is 2570. Okay, so that problem is done just like this. 674 is what instead? 675, because that's the mass. The specific heat of solid copper goes here, right? Because this is specific heat of solid water. So the temperature range, it started at 900. What is the melting point for copper? So what do? 1085 minus 1080. Okay, so we're starting at 900 degrees, right? Copper begins to melt at what temperature? So what did we do with these two numbers? We subtracted, right?
Yep.
What do you do with these two numbers? Subtract them. Then, in step 3, we took 100 minus 0 to get 100, correct?
Yep.
In this step 3, what do? We take, what was that, 2006? What's the boiling point?
2,500.
Okay, so you subtract those two numbers, and that one would go here. Then, in the final step, we're going up to what, 2,700? And we've got 2,570. So subtracting them two numbers, that would go here. Okay, so when you start putting all these pieces together, it's really not that difficult, I don't think. But other than putting them in order and not making a mistake punching in the calculator, that's the hardest part, probably. Yes. Yep, but that one with the copper, that's the 5-step problem. Okay, so what you can do is look on these papers and go ahead and pick a number, and we will work on that together. Going once, going twice. What does 7 say? And what was the volume or cubic centimeters? Okay, so with this, it's saying how much energy, correct? So this heat energy is labeled in what? Joules. So it's either joules or kilojoules. So this is going to be our formula. Okay, so we're looking for the quantity in joules, right? Okay, we've got the specific heat, that's here, correct? Then we've got a density and a volume. So what can we find with those two variables? Okay, so in this case, 1.2 equals the mass all over 244. So what does mass equal? What would you do with those two numbers? Cross multiply. Am I changing the value of 1.2? No. So what is 1 times m? M. So mass equals whatever those two are times each other, which is what? 248.
I got 292.
Well, I'm using 1.02.
What is the
Density. Yes.
1.02.
Is it 1.2 or 1.02? 1.02. Okay. Okay. So now when you cross multiply, what do we get for a mass?
248.8.
Grams. So we were also given a temperature range, correct?
25 degrees Celsius.
Okay. So what's that change in temperature? 25. So our Q then equals 248.80 times what's the specific heat?
25.
No. What's the specific heat? 4.16. And then what was your temperature range?
25.
25. Now you might say, we would have never got, well, that's why you ask. We would have never figured that out. Well, if you don't understand, that's what you got to do, is please ask. If it's a quantity of heat, we label that in what? Because somebody mentioned that already. Okay? Yes. So notice, what does it say for a due date? 24th. When's the 24th? A week from today, correct? 17 plus 7 is 24, right? I think that's how it works. All right. So, we will catch up to you next time.